Hi everyone, or hi no fun. I'm Colin Belmore, and I'm going to give a talk on my experience and my journey learning F sharp over the past 2 or so years that I've attempted to learn it. So let's get into this. Alright, so I'm not actually going to give a talk on F sharp the language. I don't think I'm qualified enough to go through and teach every little part, and I don't know if a lot of people would be interested in learning F sharp if you're not already learning it. So, hi guys. So I'm just going to sort of give a meta-analysis, like the warm and fuzzies you get from learning a new functional programming language, and all of the problems that I had learning with it, all of the things that I built with it, and sort of what I came out of it with after spending, let's say, probably an hour or two a week sort of immersing myself in it over 2 years. That's significant, right? Alright, so I'll talk a little bit about more my problems, because that's sort of where I'm motivating this from. Right now in my job I'm doing C++ and Python, and it's for streaming scientific data analysis. And I'll go into my problem space later, because that's where I applied learning all my F-sharp stuff. But I have no experience with functional languages. I went to school for electrical and software engineering, and I never learned what a Lisp was, never took a compilers course or a programming language theory course. So all of my language knowledge has been very imperative, very low level. I've had firmware jobs before I've had higher level programming jobs. So for me, Python was oh my goodness. And JavaScript was look, first class functions. So it was blew my mind. So I'll sort of just keep that in mind if you have a lot of functional experience. I'm sort of coming from a place of ignorance. So hopefully that should help other people who don't have that same experience. F sharp is also a musical note. So I will go through some basis of it, sort of give you some background on it so it's not totally abstract. It's a hybrid functional programming language that was developed by Microsoft Research in London as the best language to port to the .NET runtime. So they basically looked at all the existing languages, and this is the time that they were coming out with Iron Python, they were porting Prolog.NET and all those sorts of things. They had J, so you could run Java on .NET and all that good stuff. So they ran OCaml on .NET, and they're like, oh, this is actually cool, and it works, and it does the things we expect it to do, and we can optimize it well. So they've sort of been building it since then. So that was in 2009, and it shipped with Visual Studio 2010, and it's been included since. So it's been sort of the third child of C#, VB, and then F# included in the Visual Studio package, so you get for free. 100% open source, so it was the first Microsoft thing to go open source. I don't know if you guys follow Microsoft open source things, but a lot of their things are now taking open source. F# was sort of the poster child and sort of led the road on this. So the entire F# compiler is open source. The entire language spec is open source. A large number of their contributors for the RFCs into the language are outside Microsoft, even though a lot of the tooling and things are supported by Microsoft. So it's an interesting engagement. I'll talk a little bit about how the tooling affects that experience, because it's sort of a second-class citizen on its own platform. The only high-profile user of F# in the US is Jet.com, who recently got acquired. Other than that, most of the activity, I would say, is in London and most of Europe. So I think a third of the board members are from London and across Europe. So
why London? Do you know?
That's where it was invented. It was invented by Microsoft Research in Cambridge.
Okay.
Yep, it's on Sime. And so a lot of the interest sort of grew out of that naturally. And I think OCaml is also a French supported language. So again, that style of language is much more popular there than here. Obviously, Lisp being more popular here and MLs being more popular there. All right, so I'm just going to go through a quick feature list of things. So these are the sort of things you'll see if you go on the web page and you'll look through things. I've bolded the ones that I've found that were underemphasized, and I'd like to overemphasize now. Languages with full type inference really change your opinion on what static typing is. Most people think static typing is awful. You have to type out these types. full typer inference changes that basically completely in terms of helping versus hurting. Curried by default, I'll go into a little bit of that, but that really changes how you use the language and the syntax around it. Some types and pattern matching also really change how you do dynamic dispatch and things like that. So a lot of code that you would use objects and polymorphism for, you can use some types and pattern matching for, and it makes things so much cleaner and easier. I mean, it's one of those things where it's like if you have a language without some types and pattern matching, which completely go together, I don't know how you could have a language with one and not the other. It really changes the way you work with the constructs that you build in terms of smaller things. Obviously, there's other languages like atoms and things like that you can work with in terms of data types, but
what are some types?
Some algebraic data types. So it's just like being able to describe a type not as a single option, but as a family. Just to put it in simpler terms.
Union types, I think is another word.
Yeah, union types, algebraic data types, sum types, discriminated unions is the language F# uses. But it's basically a way to determine completeness over a type. It's that way you can be sure that you're satisfying all of these conditions without having to build a hierarchy of a parent class as an interface and then lots of children of it, where the children don't have to know about other children, and this way all the children are sort of at the same level. So that's really great. All the other things I'll keep there. I have units and measure in italics because everyone in the F# community doesn't use it, but for my domain it's awesome. And so it's one of those things on the long tail of features that they've sort of implemented over the years that really serves a niche crowd, but it totally changes the way, again, that I view and learn the language in terms of the static type system. I'll go into that a little bit more, but it's basically a compile time type check for floating point types. So if I have grams and I have milliliters, it won't allow me to add them. It will be like compile time error if I try to add grams and milliliters. But if I try to multiply them, it will know that it's now grams times milliliters, and it will create a new type, which then I can divide by milligrams, and then it will figure out all of the conversions for me. So for my domain of scientific programming, that's a game changer. I can do a lot of that in C++ templates because I'm familiar with that, but the amount of work it requires and the amount of library support is just fantastic on the F# side. I'll talk a little bit about how that interacts with C#, which is not at all, but that's sort of an interesting part. Code generation, you went over that before, all the good stuff like that, so we won't really cover that. Multi-platform support, so I think someone asked before, F# is on Linux and OS X. So obviously .NET Core includes F#, which doesn't include all of the .NET runtime, but those are some small details. So you can run mono. You can
just by itself.
.NET Core runs F#, so you can run it without mono.
You can run it.
You can run it without mono, but the .NET Core is smaller than all of .NET.
Okay.
So if you're okay with using a subset of things, I think it has basic things like file systems and other things like that.
Yeah.
So it depends.
Model even comes with F# by default.
Yeah. So
Okay.
it's one, it packages with it, and it doesn't come with
I just
things.
need the .NET stuff. That's all I'm saying.
Yeah.
If I'm going to do anything.
Yeah. So again, it compiles down to the CLR code.
Okay.
So anything I can run the CLR runs F#.
Cool.
Yeah. Oh, but all the tooling again is available on OS X, like all the type hints and compile time checkers and services. All right. This is a big slide. So, when I'm talking about F#, the actual syntax to learn it was surprisingly minimal. Like when I picked up F# and I was like, all right, I'm going to learn this thing. Like keywords wise, there's probably 6 keywords that I'd use on a day-to-day basis. The rest of it is the collection interfaces. It's all of the things where in another language it would be a for loop that has some permutation that's slightly different. F# sort of makes that building block a little bit bigger and lets you be a lot more descriptive in a lot fewer words. So that really changes sort of how I learned it. And once I became familiar with this big list of stuff, it was like doubling the size of my toolbox. I was able to think in much bigger pieces and assemble things much quicker. I compared it to Link. I don't have a lot of Link experience, but it has a similar feel of you're stringing these transformers together and you don't need to come up with these large hierarchies and these large, data flows and assigning things to intermediate variables and things like that, because you can say, take the first 10, average them, then take the first one. Those sorts of things. And it's really easy to build these things together. And I think at least in my use case of the language, I use these more than anything else. Like maybe I can't remember how to declare a class or a record or whatever like that. That's fine, because this is what makes the language powerful, in my opinion. Because once you can think in collections and data transformations, instead of building up objects and classes and being like, oh, I need to do this step, I need to make a new function, and like it changes that level of, sometimes you had to think you had to work with code, and then you sort of worked with concepts, and this changes it to that next level of working with transformations. I think that's a really big step for me.
What's the significance of the camel case versus the Pascal case?
Whether or not it's spell checked in Google Docs. So I just copied it and hit enter, and I think if it's a real word, it spell checks and it decides it needs to be capitalized. Sorry.
So
I noticed that. I didn't think anyone else would see it.
Are they all lowercase?
They're all lowercase. Yeah.
Wow.
Or yeah, camel case. It's case sensitive. I didn't know anyone would pick that up, but yeah. So I mean,
the Pascal case is reserved for types and objects.
Yes. So the functions are camel cased. And again, all of these are worth. So I'll go into the collections interface later, but all of these functions are generally available across multiple data types. So if you're working with lists or immutable arrays or infinite sequences, all of these things are available to you, and it's a really nice common interface of collections that F# has. All right. Expressions over statements. Elixir people love this as well, for what I've heard about Elixir. But it, again, another game changer in terms of mental layouts and things like that is the ability to compose things that you previously thought of as like syntactic blocks in your program. So I don't know how many times you've had to, maybe you declare something, you have an if statement to set it to something or another thing, or maybe you have a ternary statement to set it in one line. Having an if statement be an expression, and then you can just flow that through and have that be type checked to make sure your expression is consistent between the two if blocks. I mean, that's you wouldn't think it's a huge deal, but in terms of the way you use it in everyday programming, it can be a lot less mental overhead instead of having to assign things all the time. You can flow things through. Another thing I throw in here is the forward pipe operator, also familiar to people in Elixir and a lot of other languages. In F#, it's actually even more important because of the way it does type inference. To get a little bit into it, F# has a one-pass compiler. So it actually reads code left to right. And so if it can figure out what's on the left side of the code, or left to right, top to bottom, yeah. And so if it figures out what's on the left side of the code, it uses that type information to inform the next step of the compilation process. So if you keep your code reading from left to right, the type inference will help you and it will work for you. If you don't, it will not backtrack and figure things out for you, and that's when you start giving it hints and things like that, in which case it looks more and more like C# or Scala code.
Wait, so you're not just saying the parsing, you're saying the whole compiler.
The compiler.
Type check.
The compiler does the type checking while it's working through the code. And so if I had switched this statement where it was wrap compilation or wrap explanation cond info and then the statement, I would have to annotate the type of the statement return in order for it to figure out that that was the statement that's going into the function. So a lot of interesting things like that where the compiler, I mean, maybe you could think of it as lazy, but on the other hand, it forces you to make good design decisions when you're building your program.
So wrap explanation in this case takes 2 parameters?
Yes, exactly.
Okay, and is the explained result? Okay, is cond info the first or the second parameter?
All right, so I'll walk you. You're right, because this could be ambiguous. So it's a function. That's the let syntax.
Mm-hmm.
Then we have if check cond info returns a bool. So check cond is a function. Cond info is an argument, a real argument or parameter. An argument.
Argument.
An argument. Thank you. Explain positive result is another function. It takes one argument, cond info, which then returns something, I don't care what. But that type is the same between explain positive result, provide failure reason,
Sure.
which goes into the second argument of
The second
wrap.
argument.
Yes, of explain
So
wrap
does
explanation.
it always go just like at the end?
Yeah,
Okay. It's just
Last
hurrying
argument.
through.
exactly.
So it's like the exact opposite of some of the other ones that put it right at the beginning.
Yes. So it sort of flips all that around.
It's probably just because of the currying, right? Like wrap explanation, con info gets curried, and then
Exactly. So that's another thing with the default currying I mentioned before. So because you can just throw arguments onto functions as you're going along, instead of having, I don't know how many people are familiar with like the argument object, where you keep calling functions on an object and it keeps adding arguments to it.
Mm-hmm.
Very similar pattern here, except you don't need to declare your own object. You can just keep throwing things at it and it stores it as it goes along. I think this is really cool in terms of saving me typing and thinking, and it changes the layout of stuff. And again, I think this is one of those features that I don't think people emphasize enough when they're writing about cool features about languages and things like that. It's the simple things that I think make the biggest difference. And I could go into other things where it's like, yeah, they have a monad builder and all this great stuff like that in terms of the theory side. But it's the simplest stuff that you deal with every day that makes the biggest impact on a language. And I think languages that don't have a lot of expression-oriented syntax suffer from things where you can't do things like this. So, but again, my experience, so subjective, but one of my favorite things. Good stuff. All right, enough with this. I'm going to talk about taking a C++ application. So this is where I mentioned at the very beginning, which is I'm spending 2 years to learn this, and a lot of the times I spent learning it was just reading blog posts, watching podcasts, or listening to podcasts, things like that. Very, very top-level stuff. And when I decided I finally wanted to dig into it, I was like, all right, let's just build something. That's the way to learn something, right? Build it. So I have a C++ application that's sort of been a thorn in my side. And obviously I'm a primarily C++ programmer, so I built it. I think I'm pretty good at it, but it had a lot of things where I knew I could enhance it with it. So I had a lot of improvements in mind, but I was like, oh, this is going to be a pain to do, to like refactor a lot of this. So I was like, well, let's play with it in another language and see how that turns out. So I'm learning a new language and sort of simultaneously re-architecting my program over the course of 2 years. Obviously, this isn't a high priority project. And I'll explain a little bit about this, but I mentioned this before, but for my domain of scientific programming, there's a few different options like Python, Julia, Rust. Obviously, I could have done this in C#, anything like that. It's like, why did I pick to focus on F# out of all the world of functional programming? And units of measure really caught my eye in the very beginning. It wasn't as helpful as I wished it was, but it was still really cool. Strong static types was really great for the amount of tests and compile time things that it did. My second favorite language is still Python, which is not statically typed. So I sort of have that duality of when I want to get things done, I can always flip to something else. But I do like static types for this application. My requirements for the C++ OO application are heavily Windows integrated. I might have mentioned that before and bothering some of you about my problems, but even I wanted to learn something new, and it had all the things I wanted to get. So, all right, my problem. I'm not building a web application. I have no UI. I have a database that is completely separate from what I'm working with. I have basically one process running. It's running on the hardware. There's no scale out. There's no communication. There's no setup. There's updates and stuff, but it's very isolated. So I'm literally taking data from hardware that's spitting out sensor readings like temperatures and pressures and things like that. And it comes through a key value store, and I have a pub sub connection with the key value store, so every time a key changes, I get an update. I process those updates. Sometimes they come in at 20 times a second for like some temperatures. Sometimes pressures come in once every few minutes. So the whole application is reading this data in, performing scientific analysis on it, and spitting that back out to keys on the value store, where the only real requirement is that values need to come out every second in order to like keep a continuous stream of data going. So all of the performance things that you could get from tuning C++ to make it real time are just not important here. So that's why I felt comfortable sort of tackling this in F#. Again, because some of the channels are independent, I do use some parallelism, but it turned out to be a lot less important than I originally envisioned. So look into some of that. Any other things? I mean, obviously this is what I think about every day, so is there any other big holes that explaining here?
So what is it used for in general? Like,
So
what's
it pulls in the... Alright, so it pulls in scientific data from basically lab instruments. So things that would sit on a lab bench.
Mm-hmm.
I'm taking 7 of them together, and I'm saying, what does this look like if we take one piece of sample and run it through all 7?
Mm-hmm.
So a lot of it is tracking the delay of, all right, you put this sample through this instrument then 2 minutes later it goes through this other instrument and it has a slightly different result. So now you need to align those 2 results, and then maybe you need to multiply them to get a new unit. Let's say I'm taking specific gravity and a viscosity measurement. And I can take those 2 measurements again and create a 3rd measurement. I can say, now I know the concentration of what's in your solution because I have these 2 measurements, things like that. So that's what the analysis application is. It's very standalone. I think I mentioned, so it runs in like 6-hour blocks.
Mm-hmm.
So most of the time it will just be idle. When no one's running an experiment, it'll just sit there and hang out. And so it really only needs to process for things for 1 to 6 hours, depending on how long an experiment is running and how long it needs to collect data. And after that, all the data just gets wiped. All the data went to the database. The analysis application, we wouldn't even want it to store anything from one experiment to the other, because obviously you'd want them to be completely independent. You want it to be perfectly reproducible, all those good things. So some of that comes in nice with the referential transparency and things like that out of functional programming, but you can get that in most languages if you just think about it and you try hard. So I don't count that as a big gain if you know the gains of referential transparency anyway. Cool. Yeah. Cool. Does anyone here use C++ or know C++ very well? A little bit? Okay, so I won't go into like how backwards it is in terms of modern programming languages. But nonetheless. Compared to Python, so I keep bringing this up as sort of my second favorite. F# is sort of obviously less popular than Python, now that I'm talking about it. But Python's probably number 2 behind R for scientific programming languages, and sort of taking the hit of using F# is a hit. I mean, some things that are in NumPy or things like that, I'm re-implementing in F#, which turns out to be trivial, most of it, but I really like, I think I mentioned the strong type things before. Testing things in Python can be great if you know what you're testing for, but to really exhaustively test something, so that way it will run for 6 hours without a hiccup, is a very separate problem from testing it enough where I could come in and save it if it needed to, which is what a lot of my other Python programs do. Cool. Oh, easy deployment, true process parallelism. Also bonuses. All right. So I'm going to talk about my first idea. I was like, all right, I have this C++ OO program. I can just take this and put this in F#. F# has support for objects and all this other stuff like that. So, well, my C++ program is something like this. I have objects, which are boxes, and the data flows the arrows, and the little pieces of state are the circles. And so it's, it's small. It's basically trivial if you reduced it closely enough to a little web. Obviously, you can actually see the sensors. I took the names off this, but you can see all the sensors sort of being around the edge, where this maps almost directly to the hardware model. So it's very simple. Well, I thought it was a great idea to be like, oh, sensor should have object, and then each object has a sensor, things like that. Turns out there's a lot of complexity in trying to hook all those things up. So you end up just having this web of, oh, now we want to connect these 2 sensors together. How does that work? How do we navigate that? So those were the sort of pains I was feeling while doing this in OO. And so while I had a lot of good domain modeling built in and a lot of the restrictions and relationships naturally described via this model, it wasn't as flexible in the ways that I wasn't expecting to need when I first built it this way. So it's one of those long-term maintenance things. I was like, oh, this is slowly becoming what I don't want it to be. That I sort of fit into.
What's the big arrow?
The big arrow. So shit. Do I give it a? Yeah. So there's actually two applications here. One is sort of the scientific analysis library, and the other one is sort of like this program driver. And so the big arrow is basically a massive interface of every time a new piece of data comes in, it has to call the correct function on the library. And every time the library gets something, it hits a callback and things like that. So that's sort of the big interface into the program. And the way this broke down was that was the best way to get thread level parallelism. So a lot of this was the analysis algorithms were inherently linear and single threaded. And so having to serialize all of the data coming in, I still have to service my pub sub interface. I can't be spinning and waiting for a second and then dropping packets or whatever while I'm working. And so I sort of have a little pub sub queue coming in here. And so that's all it's splitting up there. I'm also a big fan of event sourcing. I don't know who else is event sourcing fans. But that big arrow is where I drop my write ahead log. And nothing hits the library without getting logged, so I can perfectly reproduce all of the analysis. Little things like that. I do have a GUI in here, but that's not very useful because the amount of data and the frequency of data that comes in is far faster. You can't see a number changing 20 times a second. It's even if I graph it, it jumps and it's not useful to see. So I'm changing some of that by displaying all of it in the database side, which is more suitable anyway. All right. So what I learned from this is that obviously having no functional programming experience, OO is really sticky just in terms of how I put things together. Like I was like, oh, I need a new thing to do something. That's a new type. That's a new object, and I make a new class, and I attach methods to it, and I have private methods to do little things, and I have public methods to expose data and all stuff like that. And F# can do all of those things. It has support for every single one of those. I can build full-featured classes, but it's just a big verbosity penalty to actually put all that together. F# doesn't like mutable data. It doesn't like having lots of class members. It doesn't like having internal pieces like this. And it sort of subtly points that towards you by making it more syntactically noisy, just so you can see, all right, well, this is a data member, and you have to know what you're accessing in your data member and things like that. So I ported a lot of the big objects. Pretty much exactly this I could port right into F#, and it has a very similar structure and call semantics and all stuff like that. But it didn't play well. Again, didn't play well with type inference, and I didn't get any composability gains. I was like, what did I get out of this? I ported it to a different language, and I learned expression-oriented stuff. I learned the collections, APIs, and things like that, but it really wasn't a big gain mentally, at least. And I was like, oh, functional programming is like this, awesome silver bullet everyone's talking about. Why is this hurting so much? Sort of my first instinct.
Why was it a problem for type inference?
Type inference likes when you have things that are derived naturally from constraints and not from specifying types. So if you specified a type and it was a custom type, if you specified your own and it was a type member, when you dot into it, it has to know what it is when you type dot. Mm-hmm. If you call it as an argument, it will figure out there's only one possible type this could be for it to be an argument. Mm-hmm. And it will then derive what that type needs to be and then pass that up the stack.
Okay.
So just in terms of building custom types versus using collections and standard values, it was a very, I would say calling it painful is maybe exaggerating it, but it was one of those things where I was like, well, for all this type inference stuff, I'm sure giving a lot of type hints, which is sort of the thing was like, well, maybe I'm doing it wrong. Sure. So that's sort of where, like, the syntax is a big hint versus when you're doing something. If the syntax is starting to hurt, maybe you're not using the paradigms correctly. And a lot of this time I was looking at this, and I was changing some of the things. I was using a lot more chaining, and I was simplifying some architecture things. But I kept looking back, and I'd be like, well, I can do this in C++. I can just implement all this myself. It's not that hard. It's not doing anything magic for me. But it's just sort of like I was looking for a mental gain and it wasn't there. And the next step was, how do I organize all of this? Like classes were always like my default, like, oh, when my awful script gets too long, now I need to start thinking about how to put these things in the classes and like make it nice and organized. If I wasn't using so many classes, it wouldn't be so bad. But what do I do now that I don't have classes to stick everything in? Do I just treat everything as a big bucket and there's sort of functions and data flying around? It's like, that doesn't seem any better. Like, how do I construct this mentally to sort of keep this organized so I can be like, if I need to see this piece of this type definition, where do I go in a file, right? Those sorts of like standard conventions, I just even reading other people's F# codes, it differs. There's not a lot of standardization on things like this, and so having to sort of rederive like very basic concepts of code organization was straight up painful for the first start, because I was carrying over a lot of my OO tendencies and doing it in a functional language. The overlap was awkward at times, and again I tried to make it overgeneral, and that again adding a lot of manual type constraints to functions was also kind of painful. So F# will automatically generalize things for you. So let's say you have a function that adds something. You don't have to specify whether it's adding an int or adding a double. It'll figure that out based on what you call it. But then the type on the function will say, when you call this with something, these two things need to be the same, and they need to implement the plus operator, basically. So a lot of it would do that for you, but if you try to do that manually, it's not as much fun. So again, putting all the things into transformations was sort of interesting for me, but that was sort of the first step of like, instead of thinking with things, think with data transformations. And that goes back to my point about collections being super important for how I use them. Biggest pitfalls coming in. The F# is built on top of the .NET runtime. It's not a functional runtime. There are mutable arrays. There are side effects via C# functions. There are lots of other things under the hood that you can play with that totally aren't like super friendly. There's lots of edge cases you can run into where I would say the most ink for like the C# docs or the F# docs is for C# interop. The number of keywords dedicated to making sure you can call things like delegates and extending functions, things like that, is far larger than the actual core of the F# language. And that just shows you, even though they tried to make it fit perfectly in the .NET, it's a little bit of its own island, which sort of hurts when you're looking at things like tooling. If I wanted things like code coverage, like they have that like built in for C#. F# I think you have to get a secondary plugin for. And again, things like events. I was like, all right, F# has first class events, things like that. Those made me quickly fall into the OO paradigms again. And I sort of didn't know what I was doing when I had all these tools with me. And so I was sort of just throwing things at the wall and being like, does this work? No. Does this work? No. Does this work? And so then I eventually ended up with events connecting these objects to like make it a little bit more functional. But then that ended up getting messy. So I'll go into that next, because I was like, oh, I have all these events now connecting stuff to try to like alleviate my pain. And I sort of thought of it like a DI framework where it sort of dropped in my data and then I could sort of keep things separated. I was like, oh, what's the next thing? Functional reactive programming, clearly. Let's just go all out and let's learn the most difficult stuff I possibly can. And so I started pulling in stuff. I started pulling in reactive extensions by Eric Meyer, and I was like, all right, let's see what I can do with functional reactive programming. Maybe this will help me get out of my OO worries and things like that by making things more functional. And I was talking before about things like streams, and obviously I think streams and functional reactive programming sort of comes to mind after immersing myself in the functional world for 2 years. So I was like, oh, this seems like an obvious choice. I wanted to make data more accessible, replace a lot of the patterns I'd worked with. I didn't know anything about lenses yet, so I was having a lot of deal with like data access. I was just having something change, I would fire events and things like that. A lot of things I was like, oh, that FRP is going to be my OO killer, right? So I was like, oh, I'll just take that same thing I had before and it'll stream data, right? So it's a lot of arrows. And it's the organization here, I was like, oh, seems like a lot more components to organize, and I have to keep track of which one, and I have to synchronize them between multiple levels, and I was like, oh, I don't think I'm doing this right. I sort of picked it up, and I was like, I think I bit off more than I needed to work with. I was picking up this very large methodology. I don't know what I'd even call FRP. This very large system, and saying, oh, to fix my already overloaded system that has OO and FP and all this other stuff, I just need to stack one more thing on top of it to solve it. I was like, oh, FRP, let's try this. And I just couldn't get to work. I actually went backwards in terms of testable functionality. On one hand, I actually wrote more tests so I could prove that I went backwards. But other than that, it was very difficult to get a mental model. Again, I was still stuck in the objects talk to each other. One object calls another. Maybe it's an inheritance. Maybe it's it's composed as a member, things like that. And it was a lot of mental effort to even get into the idea of working with data streams and being able to put transformers over it. Coming back to it a little bit later, once I have a little more experience, it makes more sense, and I could see obviously what I was doing wrong. But I would not recommend jumping into FRP if you have no experience with functional programming. I found it a big... If the smaller pieces of functional programming were mind-bending, this would qualify as like mind-blowing in terms of the amount of mental shifts and gymnastics you sort of need to take from where you start to where you go. I think there's a lot of power there, but it's conceptually it requires a lot more terminology to even make sense of. So all stuff like that. Just lots of little pieces is what it broke into. Cool. So that's where I am now. I was like, all right, so I have all those things. I actually undid some of my FRP work, but I kept all of the things that I did to make it work with FRP. So instead of working with streams, I was now back to working with just functions. I was like, all right, let's work with simple stuff. Functions are cool, nice and simple. Some more block diagrams. So we had what I had before. Instead of all those circles being a whole bunch of different stuff, I just have all the circles in one thing. And this was sort of how it ended up. This is how sort of it bubbled up. So instead of sort of starting at the middle and sort of designing my objects and being like, oh, I know this first detector has to talk to the third detector and the temperature sensor, and then making sure my objects could talk like that, I sort of delayed all of those decisions until the very end and just sort of assumed at the lowest level that I could pull in all this information as I needed. So instead of keeping all of the data at the object level, sort of at the edges of the graph, I just had it bubble up completely. So you could sort of think of this as keeping everything in the database and pulling it out as it needed to be. And that's sort of what it turned into, was a database that could store more than just relational, non-relational things. Because I could store things like functions in here and things like that. And so everything was literally messages come in, updates, big state, messages go out. And in terms of the top level, this was trivial to think about. It was very, maybe it's happening 200 times a second. That's fine. I can at least follow the execution every single time. The stack trace was manageable, at the very least.
Is analysis agent pure?
No. I mean...
So it's got internal state?
So that big thing is the internal state. So the analysis agent is all of the state.
Is it building it up from the input agent?
Yes.
Over time?
Oh.
So it sort of starts with like a blank default where everything's sort of empty. And then the input agent just feeds it data.
It fills it up and reruns it?
It fills up all the parts that needs it, yeah. So, because some of the parts some of the parts are dependent on other parts. So the order in which you fill it is also important. So things like that is sort of... So I sort of skipped the agents and actors idea, but obviously this is where it comes in. So before, where I was where I again had to pre-plan which parts were going to be asynchronous and things like that, using a queuing model like this, it becomes obvious. Like, I mean, even if this ran in one thread, it wouldn't change the way I architected it. But in the way this works, I can just have the agent running and spitting things onto the queue.
So when you say the analysis agent has sort of a lot of state, are these just like a bunch of let-bound variables in the...
It's literally a single record. So, and
okay.
the record is then nested. So then at the top level, it's, so I sort of tried to draw it here. So maybe the top level has 3 records, and those 3 records one contains 5 records, another one contains 3 records, another one contains 2 records. Each of those records then maybe has 5 or 10 fields, maybe 2 or 3 collections each. And so so instead of doing any objects, everything was just in this single data-only structure, where all of the work that went on the structure was totally separate from how that data was actually organized on the way up. So I'll sort of talk about that a little bit.
So when's the analysis happening?
Every time something comes in.
But is it happening inside the output agent or the analysis agent?
A little bit of both. So sometimes the output agent will be like transforming it into a different format. So let's say it needs to be in percentages instead of decimals, things like that. Most of the logic is in the analysis agent. I sort of made it big to say that's where most everything happens. The input agent's really just to make sure I'm reading my queue correctly, and the output agent's make sure I'm just not blocking on writes. It's sort of a throughput thing. But in terms of how that breaks down, it was a huge conceptual gain for me once I broke out of that OO model of being like data and the methods that work on it need to be next to each other. They need to be completely related. In terms of doing that, I sort of flipped it a little bit. So I was taking this data and I was sort of iteratively unwrapping it. And at each layer maybe had a little piece of data to tell me how to unwrap the next layer. But it was very obvious how many layers I needed and what the next layers would be and things like that.
Can you give an example of the layers? I'm having trouble.
Okay, so let's say I'm converting voltages to an absorbance because I have a light source and I have a laser shining at it. And I need to know how strong the laser is. I need to know how much voltage I'm getting off my thermocouple and diode for my temperature. So I'm having to pull all of these things together, these 5 pieces of data. But each of those pieces of data, they need to be processed together, but they aren't actually interdependent. Like I need to do all of that processing every time a new sample comes in, even though I'm working with 2 or 3 independent pieces. Does that make sense? I'm trying to be abstract here. I'm realizing it's...
Yeah, can you be more specific?
Yes. All right. So for one of these, I'm taking the whole history of one of the sensors. And I'm saying, look at the last element of the array and look at the baseline value. And I want you to subtract this historically recorded baseline value from the newest value so I can see a different signal. So I'm basically normalizing the data as it's coming in. But to do that, I need to pull the normalization value, I need to pull the conversion value, I need to pull the previous values, I need to pull any other state information that would change any of those things. All of those 5 things are stored individually somewhere. And obviously they're all related, so I'm putting them all in the same record. But when I'm working on them, I split them up as I go. So when I'm pulling it in the first module, I'm saying, all right, now I have my voltage, I have my conversion factor, and I have my time. And so one of those functions looks at my voltage and my time, and then says, do you need to interpolate over your past data? Maybe you missed 10 seconds of data and we need to draw a line to make sure you have consistent sampling. And maybe another function is saying, hey, let's take this data and let's do something with it. Let's multiply it and then add it to this new set. All of those things sort of come out of one struct and I'm sort of pulling them in, but I don't need to work on them together. So instead of, in another function, I would have this like serially ordered. And I would say, all right, do this and do this, even do this. even though the order of the functions is irrelevant, like they're idempotent. It doesn't matter the order you operate in them. And thinking about that main objects before, I was like, all right, well, I still have to call them somewhere in an order. I can't say the unspecified. But in terms of unwrapping the data, in terms of, how would I say this? What's the saying? If you have cohesion versus coupling. So when I think about that, it's a lot of these values are loosely coupled because I can pull them out anywhere. They're not tied to each other in any way other than the fact that they're in the same record. But they're cohesive because the only thing that I'm working on them with is the thing that's updating them. And so I can't update, I could, but I'm not updating values that I'm not reading or that I'm not pulling in.
Sounds entangled.
It does, because it's one of those...
Not efficient. And so therefore you can't scale sensor-wise. I mean, that's just...
Well, it's perfectly
like
scaled.
when you say something like that.
Well, because I'm always reading what I'm writing. Because I'm never working with data that I don't already have. I start with nothing. Right? And so I'm always saying, I'm taking new data, I'm working on it, and I'm producing a new set of data. And I always need that old data. All that history is the core of the program.
I got it.
So when I'm pulling that in, it simplifies it where I no longer need to keep track of where that data comes from, what other things were happening at that time, what other pieces. All of those things are arguments of my function. I no longer need to have a lot of constraints on the rest of the system to say the UV sensor can't be faulted. I have to be in a pump flow rate that is this. All of those things are arguments that I'm specifying. So instead of taking the responsibility at the lowest level, I'm always pushing the responsibility up to the caller to satisfy the arguments. So in the way that makes it so at the lowest level, the business logic is trivial because I'm saying, make sure this happens. Here's my type to make sure this happens. And then work your way up.
So I have a question.
Yeah.
Is this something that you could, in theory, solve by just reading all the data and then doing a pure function over the data?
Yeah.
Yeah,
So
there's no interaction with the environment, like you're controlling the experiment somehow.
Oh, yes. So
Because
I'm
you are.
yes. So a lot of the analysis, the keys I'm writing back, are read back into the hardware that then controls it.
I see. So, okay.
So as long
It
as
is real time. Like it
yeah, it's soft real time.
Sure.
Yeah, because a lot of it is it won't need that value maybe for another minute, because maybe it only makes 1 minute steps or 1 minute intervals.
Some diagram at the very beginning when it was data was coming from the sensor, you don't go all the way back there, but it was then going through the thing going into the database. There's another arrow going back into the sensor.
You said not go back there, but I did.
So, yeah, so
All right. Yes.
This is a one-way sort of diagram. But
Yeah,
you're saying
so-
it's not.
So there's another agent to the key value store that will then read these data pieces I'm talking about. But that's, yeah.
And influence the
Do what?
future.
That will then influence the actual hardware that the hardware interface then reads. So
where are you storing those? On the sensor itself?
all
Where's
of
this happening? Because
this is all in memory, 100% in
okay,
memory.
I get this, but on the sensor?
Oh, on a PC. So the sensor connects to USBs and a whole bunch of stuff,
Yeah, okay.
and it just sends it over. So I could talk more about the interface protocol. It's actually using Win32.
No, I mean, I've been writing software for a long time, and it looks like turning functional programming into Fortran in a lot of respects.
Yeah, well, because Fortran gives you that, like, this is the data,
Yeah,
take those steps.
No, I know, exactly.
And sort of flipping that around to saying, because I have this awesome type system,
Right.
I no longer have to worry about keeping track of how my data is stored. I can keep track of what I'm doing with it.
But it's very procedural.
Absolutely.
You know,
So it has that procedural element where I'm now isolating all of those
Right.
processes.
No, I got it. I mean,
Yeah.
I understood the whole thing. It's
Yeah.
just, and you know, coming from a purely computer science background, you know,
Yeah.
it's the antithesis of what I'm taught. You know, so
That's what I
because
thought.
it's not, you know, it's not. It doesn't meet formal language, if that makes any sense. It works backwards.
Works backwards.
In formal language, yeah. Instead of trying to, that's the whole idea behind abstract types and generics and those type of things, right?
Yeah.
Is that you're trying to generalize with your language,
Yes.
and now you've taken some, you know, functional as opposed to being logical, even high, you know, even taking, you know, even more abstraction with that. Now
Mhm.
you're working kind of backwards, and
Yeah,
that's,
well, I'm starting from
so you're taking like a C mindset or assembly mindset,
and working up.
Yeah.
Yeah. And so I'm using
So
the
that's
type
totally
system
crazy for someone who comes from a computer science world.
that you would take
Yes.
the business logic and work your way up.
Yeah.
Okay.
I mean, you want to abstract.
Yeah. Yeah. Yeah.
I mean, the idea is to get, you know, at least what I was taught, you know,
No.
get as abstract as possible.
And that's a
You know,
lot
so
of
therefore, you know, an
You-
expression is simplified and not complex. Right?
Yeah.
I mean, the idea was that, I mean, we're not throwing switches anymore, right? I mean,
we're using these bigger pieces to do
Yeah.
all of our work.
right.
And until I started doing this,
Mm-hmm.
I was like, "Oh, this is so messy. It's like it could be
Yeah.
back to spaghetti code."
Exactly.
But then once I started working with the way that I mapped over and composed functions,
Uh-huh.
I realized I was writing my domain language in a higher level. So I was saying at each lowest level, I still have to do my multiplication, I still have to do my addition, all stuff like that. But now I had a word for it. I was saying process UV data. And process UV data takes UV data and new sample. And then I can process that into process all samples. And process all samples takes process UV data, process viscosity data, process viscometer data, process all these things. And that becomes just process inputs. And it's sort of mapped over all of that in such a clean way that all of the abstractions I was building in OO just seemed overly complex for what I was trying to do. I was simplifying my domain so I wasn't building abstractions over the data that I was thinking of. I was building abstractions up from what I was working with. And then because I had such powerful tools to abstract that, refactoring was trivial. If I want to say I'm adding this new function to connect these strings, composing functions that did that was so much faster than having to write 4 different interfaces on 3 different objects to connect those pieces. Because when my common language, my common interface was the collection functions I brought up before, it changes how I stored and represented my domain data into values. I wasn't talking about a UV sensor that spits out UV data. I was talking about a list of floating point values.
Right.
And so it really
I
flipped my
got
mind.
the whole thing, and
Yeah.
but again, it goes back to, you know, when you start abstracting, the end goal is to get an expression that's would be generic to the, you know, all the inputs, not a specific expression. And so again, you know, it goes back to all the, you know, you're taking each data type, you
Mhm.
know, and then specifying, you know, a specific value for it.
Yes.
That's not abstract.
No.
No, it's not at all. So,
Yeah.
I mean, I've done plenty of assembly programming, and
Yeah.
I'm completely comfortable with it, you know,
Yeah.
putting, you know, hashing algorithms on ASIC, you know, EEPROMs and stuff
Mhm.
like that, you know. Even just a couple of days ago, I took, you know, BIOS and, you know,
Mhm.
got a USB programmer and started. And so, you know, it has its place.
Mhm.
I'm just trying to think how functional programming is going to fit inside, you know, because, you know, I still work with both the assembly side of
Mhm.
things, and then, you know, I you know, haven't, you know, used I would say, functional as much as I would like, just because OO is kind of the king when it comes to web applications, even still today.
Yeah.
I had a discussion with my colleague here, Eric, about struggling with some of the things in JavaScript that claims to be OO.
Yeah, and it doesn't map as well to forms and things like
right,
that.
exactly. And I want to jump off of a cliff.
Claims to.
Yeah,
Yeah.
it claims to be everything, by
Yeah.
the way. I'm not going to say that it claims to be one thing, it claims to be everything. But, I'm just interested in, because I really want to see what did you start off with? Did you start off with C++, or did you start off with C, or did you start off with assembly when you started?
I started off with C++.
Okay, so you didn't even. Okay, so when you were doing C++, and you were working.
You mean for this program?
Yeah, for this program.
Yeah.
I mean, you were creating templates, right? Right, and you had objects and those type of things. But I'm kind of curious as to, were you sticking to the object-oriented methodology, or were you breaking down into C? We're still using pointers. We're still using.
So when I said C++ 14, I have no news. I have no mallocs. I have no. I have some references. I have no raw pointers. Everything's. I love smart pointers. I love auto. All the great stuff like that. But again, one of my biggest gains from using this was the standard template library made more sense. When I was using things from a standard template library before, I was like, oh, accumulate's a bear to use. I have to give it the start and end pointers, all stuff like that. Coming from this, I was like, oh, that's like a map. I'm now applying this function over these things. But the way that C++ has you use those things is a bear. It's awful to use those things.
C++
It's retrofitted.
It's retrofitted for C.
Can I ask something? So does F# have stuff like type classes from Haskell?
No, it does not have polymorphic functions. Doesn't have higher kinded type.
It does. It doesn't have like type classes.
It doesn't have type classes. Okay.
Yeah.
But it has,
yeah.
type variables.
Yes, it doesn't have polymorphic variants.
Okay.
Sorry.
Okay.
Yeah.
Interesting.
Yeah.
So
So
I'm wondering like how much you can do with category theory and stuff.
So there is some of it, but I wouldn't say it's discouraged, but like a lot of the limitations of F# being on the CLR are sort of built around doing type classes is expensive because it literally has to exhaustively test these things. And they're looking into ways of doing those, but like there isn't a lot of pure abstract programming the way other things do it. It's very much create your domain of these smaller bits and then make sure they lock together tightly. Yeah.
So do you think you've overall gained value out of using F# over C++? I guess that would be the...
Absolutely.
Yeah, okay.
It would be the learning of how to work with data in this way. So it was learning about... Because before it was always... encapsulation, make sure you hide your data, provide law of Demeter, all those basics of like the OO way to do things, because if you don't do that, it's a mess. And a lot of the immutability guarantees in F# fix that, a lot of the type guarantees in F# fix that, a lot of the abilities...
Just like abstract data types are way better than class hierarchy.
Yeah, it just blows it away. Like it's not even... It shouldn't even be a thing. I think I saw someone... You shouldn't be able to say your language has type safety as a feature if you don't have abstract data types. It's one of those game-changing ideals where once you have that knowledge of, oh, I could do this way, it changed the way I built programs in C++, it changed the way I built programs in Python, it changed the way I do some JavaScript. It gave me a new perspective on what I was getting. I'm sort of spoiling my ending.
Well, that's okay.
Yeah. So that was going to be a finale.
It's all right.
Yeah. But, so to go back with my first problem of how do I organize things so it's not a spaghetti monster, things naturally fall into this format. So before I mentioned before that F# has the one-pass compiler. If you don't declare your type before you use it, it doesn't know where it is. So it makes it really easy to be able to say, declare your types, declare your functions that work on that type, and your last function in that module has to be the one that uses all the functions above it. And so reading top to bottom, you will literally read inside out of all of your data transformations. And so that once I figured out that that's the natural way to structure it, and I wasn't jumping around and having to be like, oh, in C++ I would have an anonymous namespace, and I would have private functions, and I have public functions, and I would have static functions. I don't need to pick which one it needs to be if I know which order it's in, because that automatically tells me its data dependencies, it tells me what else it could be using, it tells me what else can be going on. And sort of that very simple thing, I was like, oh, well, it seems obvious in retrospect, but I didn't read this anywhere. And all the books and all the blogs I read, they told me every single thing about the syntax, told me every single thing about, category theory and what a monad was. Never went over, this is how you structure your file so you can read it. That's in Code Complete with C++ and stuff like that.
Can you do mutually recursive functions?
You can. So the and keyword in F# is mutually recursive things, which is strange because most people use and for binary logic. It's one of those weird edge cases. Yep, and you can keep doing and it'll make them all mutually recursive. It's funny, but yeah. Yeah, but there's also a recursive keyword. It will do tail recursion if you mark it as recursive. I'll do the tail call optimization. Again, it's F#. I want to say the keywords to start off with are small, but it is full featured if you go to the edges. Like I said before, it does full C# O interop. It does full. You can do a lot of optimizations with mutable data types and procedure programming and all good stuff like that. So, in terms of power on that side, it's not lacking. So yeah, I sort jumping back to our conversation before, literally going back to the basics. Like, how simple can I make this so my logic is obvious, that my data transformations are simple, and then my whole program is just straight up shorter. I'm not trying to build this massive thing to be like, oh, this is extensible in these directions that I think I need, I'm probably going to need. I'm just working with the data I have, and then saying, I will decide my component action as I need it. It will go up and say, I've defined these sort of base level to talk to, and now that I have these easy functions for composability, I don't really go over function composition, but once I figured out what function composition was and how to chain things together, it made putting smaller pieces together into bigger pieces trivial. Instead of having to come up with abstract patterns of factories generating other things and having another delegator pattern to sort of swap between multiple things, it wasn't even an object. It was like a function with two lines, or it was a single if statement to switch between things. And so I cut down a lot of my overhead with good data structures that made sense based on very simple things. The data structures were really well typed, as I mentioned before about the units of measure. I couldn't screw up. I couldn't pull in a data structure of voltages and use it as a data structure of, temperatures. That was great. And then concise functions are just natural when you don't have this backing framework that you're hooking into, which is sort of where I was headed in C++, was trying to make sort of this general framework. Instead of that, I'm just building my application and let that be the framework. Sort of my idea. But the immediate gains was, at least from my FRP screw up, was simple code. I wasn't using anything else between for, let, and maybe some other things. But there's maybe 5 keywords in most of my code. And it was all call a function, do some math, call another function, do some math, unwrap and rewrap records. It was only later that I learned about lenses, and lenses, again, changed the way I'm going to go into. But has anyone done a talk on lenses?
Not here, no.
Not here. That blew my mind once. I was like, this is a huge pain to unwrap all these records. And that's people have figured this out already, and it's a whole... Turns out that people are really smart and figured all these things out long ago. Mutability problems, I didn't even mention the big problem that was in C++, but const isn't what you always think it was. Even though you sprinkle it everywhere, I try to be safe. And logical errors are more visible as type problems. So to sort of skip ahead a little bit to the cons, when I thought of types before and strong types, I was like, oh, people keep talking about this thing where if I keep all of my types consistent, then once I finally get it to compile, it's just going to work. I never had that experience. I could still screw up all of my logic within values and still have my business application be wrong. Even with all the type safety options, it's still wrong. You can still do stupid things when things are the same type. You can still put things in the wrong order. Off by one errors. Even with things like, I could do like try get head so it returns a maybe instead of just throwing an exception. Things like that sort of helped. But just all of like the things that, unless you're in a dependently typed system, you just can't prevent. Empty lists, for instance.
I think my theory on that is that it takes 2 hours to compile to like fix all the bugs, and you get it to compile, and you can't even remember what you were trying to do.
Yeah.
And you're just so frustrated, you just want it to work so much that
Yeah,
say it works.
You're just like, oh, this works, right? I ran my test and my test didn't crash. Does that fail? Yeah. Yeah, but another part about, did I mention the tools? I don't think I did. So the nice thing about it is, I mean, most editors now will have like syntax highlighting for like, you screwed something up, fix it before you even try to compile. Having types to do that meant I had to write fewer tests to get the stupid errors. Because in Python, in order to like suss out all of the things where I typoed a attribute name and then it just fails because I didn't access the attribute out of 9 out of 10 tests that I wrote because I have 95% test coverage, and the linter doesn't catch it because it can't because it's a dynamic attribute name. The type system, just having the basic type system, again, can save you from that. And it was sort of a strange thing where I didn't expect to be able to say that, but after I ended up looking back, it should have been more obvious. I think I sort of mentally, the abstractions I built up with those types made it easier to organize things. So instead of having to come up with these larger systems where it's like I had to have a map of the system to see where I was and how things interacted, the abstractions told me all of that like through their type signature. So documentation was a good bonus, but it was sort of like the easy abstraction once you have types saves you a lot of time. Surprises. So these are things specific to F#. So sort of going deep on this one. Function parameter order matters. Like that never would have crossed my mind. But once you have the curried by default, the order of your functions is now the order in which they're curried. So if you want to make a function where you're changing the one variable a lot and one parameter a lot and the other one's very infrequently, that one should be the last parameter. And that way you can partially apply the first 4 and then just keep folding over that function maybe and apply the last one. Little things like that I was like, oh, someone really thought about this. And a lot of functions, like the standard fold lets you throw in functions like that to do these things. I mentioned before the pipe operator, that changes everything. Pattern matches to reduce error handling. It's huge. I mean, literally just the maybe or option type changes things where it's like before you had to have, if you returned a double, you either had to return a sentinel value, you couldn't a bool along with it, you had to throw an exception, you had to throw some other out of band thing that you could possibly fail. And pattern matching, or obviously the algebraic data types and then pattern matching lets you completely map over your error types that way. Cool. So sort of recap on OO. I don't think my OO solution was wrong in any sense. I could probably keep going, and I probably will. But I just sort of wanted to try something different and something that wasn't the OO solution. And so while that's what I started with, I very quickly realized that if I wasn't working in a object-oriented language, I should make an object-oriented solution. So it was really the perspective I got from building things that wasn't OO and that wasn't heavy on mutability and that wasn't heavy on, duck typing and things like that. And so picking a language that was the confluence of those sort of let me try out new things. And looking back on it, it gave me that perspective on OO to be like, what was I really doing? What was the motivation behind these? Because a lot of those things you pick up of, oh, this is the way it's done. This is the way it's easy. Oh, I had this awful problem in the past. Now I always have to make sure I'm using accessor attributes, things like that. And coming from a language where you don't have those concerns, you sort of start questioning why people made those decisions in OO and whether or not that's always sort of the dogmatic approach you should take when building OO applications.
So do you feel that FP has made you a better OO programmer?
Absolutely. Because a lot of it is questions where I'd be like, oh, this is an object, I put new things in it, I make a new class.
30 members and
Yeah.
100 methods.
Well, it's not even that. Maybe it would have 100 methods, but maybe I would have 4 classes delegating 4, and I'm like, nah, I don't need that central function. I'm just going to use those 2 objects directly, and if I need to extend those, then I'll extend those. But I'm not going to try to overgeneralize and make sure that I'm keeping like a perfect separation between things. Like I was always a big fan of law of Demeter. I was like, all right, more than one dot on a mutable function or something like that, problems. Because I'd gotten bitten by that a lot in really old OO applications. And so I was like, this is the way I always need to go. But then looking at this, I was like, there's no reason to do law of Demeter when the whole thing's immutable. It doesn't make sense anymore. You can dot into whatever you want. It's not going to change while I'm doing it.
What does dot into mean?
Like dig deep with like method
Chain. Sorry.
Okay.
Dot is the...
So doing that is bad if it's immutable?
Yeah, because you don't want to be accessing people's private mutable data members if you don't know what they're doing with them. And things that rely on other objects' private mutable data members will break in terrible ways if you don't have tests exhaustively testing all the interfaces.
going
Oh,
deep.
accessing private fields?
Yeah, well,
It's not private, but like you're depending on
The chain to stay the same.
Of something, because you're going deep down into the like,
They could return a derived type that still matches your type signature and doesn't break any of your code, but doesn't work the way that you intended to work.
you don't want to change one thing in your application and it accidentally breaks something very far away. You want to know, you want to be able to either abstract all of that at each level or to be able to say you can't even reach that far deep. With types, you run over some of that where if I was reaching that far deep and I changed it, as long as I changed the type signature, it would break and I would know that I needed to update it way over here. But it's sort of just like it's an organizational pattern, I'd say. Organizational sanity. Yeah. The other thing is, doing all of this is still difficult for me. So I don't do this like every day. This isn't my full-time thing. So being able to go through and like think about this and get in this mindset and build these pieces is not an easy task. Like actual writing the code and knocking it out, that's still pretty easy. It's getting myself in the mindset of organizing these things, how to compose things, what's a good way to compose things, how do I pass functions around, things like that. Because once you have a different set of toolbox, you have a different set of primitives, and you're literally speaking a different language. It's not like the difference between, Java and C++ and C#, where they're all essentially equivalent when you're talking about building systems with them. It's the difference between building an assembly and building in Lisp. It's totally different ways of looking at what you're trying to do. And it still requires a lot of thought per line written. And so a lot of it is, I only wrote 5 lines and this is a really short function. But the equivalent function I would have wrote maybe would have been 50 lines. It would have taken me just as long to write. So it's sort of the time trade-off. I haven't quite got that far yet. So.
Do you find it easier to read functional code than OO code?
Depends. With OO code, I have to read a lot of it before I can really grasp what's going on.
I guess you're still very comfortable with procedural code.
Yeah, I do a lot of C assembly things, but like when I'm reading a chunk of C code, a lot of it is, all right, where does this pointer come from? Now I have to go find it. Where does this object come from? I have to go find it. Where does this other thing come from? Who sets this member variable? Now I have to go look all the things that set this member variable. In functional, your scope is so much smaller because you're primitives are bigger, and so you can say a lot more and make a lot fewer assumptions in the same amount of space. And so then that restricts you on what you can say, which is why I think it's a little bit harder to write. Because I can't say, oh, grab this thing I computed 2 minutes ago. I have to say, go to the place where, or go, make sure I get the value that I got from 2 minutes ago into this function. And then I have to go and thread all of that through. And that's still, I haven't quite got around that pain yet. Yeah, that's where I would take that.
You have an example of, something that you took from C++ into F#? I'm just curious.
Like code or like an idea?
Yeah, code.
Oh, I can show it to you, but it was a work project, so that's why I didn't have any code.
Okay.
So I'll give you some gratuitous stats at the end that are generalized. Yeah, but one of the things I realized with this is that even if C++ has all of these functions, every time I wrote all these things, I was like, I could have done this thing in C++. It won't matter. It's the way that the things that are easy are what you use. You do what's easy to do in the language. I'm not going to do backflips to make sure I'm doing pure functional programming in C++. It's possible. I do it sometimes. It's a huge pain. You do what the language makes easy for you. You do what requires less syntax. You do what requires, fewer characters, fewer abstractions to build. And that was the big gain I got out of this. So this was a clean slate rewrite, sort of come back to it. So sort of mapping that original object domain to the same object domain was sort of a misnomer because I knew I didn't want to do that. So it's sort of like when you're doing a rewrite of something in a different language, taking all the things you did before makes some things easy because you obviously don't want to change everything. You don't want to really start over. But you also bring all of the same problems that you had with you. In which case, if I would have kept my first solution, it would have been the worst of both worlds. I would have been doing mutable OO work in a non-mutable OO language. It would have been awful. And so sort of reconsidering those assumptions and sort of building anything that's... my total lines of code for this was about 15,000, maybe 20,000. My C++ code base was about 35, maybe 45,000 lines of code. So they're both like trivial sized programs, but like building anything bigger than that, I think is more than you can keep in your head for like trying to like keep it simple enough to port. So porting big programs is obviously harder. Obviously I didn't do this as like a full-time job porting, so I wouldn't recommend that either. I think it'd be very dangerous to say functional programming is the future. I'm going to rewrite my whole business in it. Because that would turn out terribly for me. New appreciation for the thought process. As I said before, 70% lines of code fewer, obviously. Just like the lack of curly braces and syntax changes drops it more than half.
Actually, can I ask a quick question before I forget about it? So, I mean, how easy is it to call like a C++ library from F# or F# from C++ if you're using like .NET? Is that not something you do, or is it?
It's totally possible, and things I've avoided on purpose.
No, that's fine.
Yeah, so I do call native code from... Actually, I wrote a C# wrapper, and I call native code from the C# wrapper, and then I call the C# wrapper from F#.
Okay, because that's what I do too. I have C# on the outside, and then F#. I think I use F# more.
Yeah.
I do it every day, but
yeah.
Yeah.
So the native interop, was nice, but a lot of the C++ functions that I was using, if I was copying stuff over to have it garbage collected, it'd be awful. Yeah. So a lot of stuff that I try to copy the inputs once and then keep it all there.
I see.
Yeah. Which is that message, so that big arrow I had before would have been that. Faster. So this is something that I think surprised me when I first ran it, is that if you're doing less work, your code will actually run faster. But actually, a lot of this came from, I was using Qt, which is a C++ library, to do some of my threading. And the Qt library is not made for real-time data streaming like this. So just replacing that with a thread-safe Q was most of the speed up. And again, this runs way faster than real-time for most stuff, so it actually doesn't matter. More memory. It should have been obvious. VMs take memory. Overhead of keeping objects around take memory.
Only 20%, that's pretty good.
Only 20% is pretty good, but the way I was storing data changed significantly. So because I could keep a lot more guarantees around my data, I had a lot less debug data. I don't know how else I'd call it. A lot verification data. So because I could eliminate things like pulling data in with the wrong time and then appending it to the wrong array or something like that, I simplified a lot of how I stored my data.
Because of the types?
Yes, just because of the types. And because of the types and because of the way I was organizing it in the records.
So you have less memory, but it's taking more RAM. You have less data, but taking more RAM.
Yes, which is the overhead part. And again, I mean, the whole thing, at max, this maybe takes a gigabyte of memory after 6 hours worth of stuff. It's not huge. Because a lot of stuff, I'm pulling data in and I'm compressing it to 1 second intervals. We're not compressing it, but filtering it, resampling it to 1 second intervals, because that's the business domain. So, happy developer. I enjoyed this, so that's why I could do it for 2 years as sort of a side project, but it changed my way, because I was like, oh, C++ is awesome, I use it all the time, maybe I'll learn a new thing, but I'm really probably going to use C++. Using this, I was like, C++ was a ton of work I was putting into it, and maybe I could get complete control over whatever I was doing, and maybe I liked the fact that I could do hoops with template classes and other things like that. But the simplicity of F#, which isn't something I'd normally say, is far greater than the loss of control you'd get from a lower level language. So that was a big gain for me. That's it.
So, I got a couple of questions. First, would you say that F# is a good language for somebody who is new to functional programming?
Yeah, I mean, for me, it sort of was, only because I could do that first stupid step of just importing everything.
Yeah.
And it sort of helped me learn the syntax, helped me learn those collection functions, where I learned all of the, I don't want to say the easy parts of the language, but I learned all of like the typing habits very quickly. And then I could figure out all the more complex conceptual stuff later. So I could sort of punt on any of those higher level abstractions until I was more comfortable with them. Because a lot of it was, I would do something, I'd write this awful function, I'd be like, God, this is awful. And then I would like look up how to make this not awful. Like, how do I keep this function around? How do I pass this new function to multiple things? And then I would look up and read, and it turns out that's like a super common problem, and like, they have lenses for this, they have all these different, libraries available for it. But I wouldn't be able to learn about, lenses wouldn't have made no sense to me had I learned them without having a problem of expanding and collapsing records. And so sort of getting a start of just getting your foot in the door, I thought F# did a great job at that. Only because it did have some simple constructs, and it was familiar on some level, because I could always reach down into like the normal .det. I can call like system.datetime or system.triparse or double.triparse or stuff like that. So all of the .NET things that I was familiar with were just like in import away all the time. But sort of weaning myself off of those was, I think, helpful.
The second question is, you mentioned SQL and LINQ, and that piques my interest because I do have a good bit of significant amount of experience in SQL and in LINQ. So would you say that functional programming and F# in particular is a good language to, for somebody who understands those concepts well? Does that help for someone who would want to learn functional programming? Is that like a good point, or that somebody who was new and learning functional programming could tap into?
I mean, I found it, I'm not a SQL expert. I've used SQL Server for a few years, pretty good at writing queries, but I would say the way of thinking about sets of data as opposed to individual steps, once you can sort of think in I need to do this, I need to take, skip every other one, now I want to convert it, all sorts of things. And the higher level of data abstraction was really helpful. And I think F# provides more concrete methods than what SQL does. SQL obviously does a lot of magic for you. And F# makes that a little bit more explicit, and it's more eager than LINQ.
Yeah.
So you're not going to get the same optimizations that LINQ can do.
SQL is designed to work on large sets of data, and basically a lot of what you do is you figure out what you're going to do to one record, and then you figure out how you're going to apply that rule or process to to a whole batch of records. And SQL takes care of the batch part for you.
Yeah, so thinking about that in a functional context would be you write your function that takes one value and spits out another value, and then you can then take that and map that over a collection. And it will transform one collection into another collection, or it will transform all the values in that collection, something like that. So I think once you start thinking in the data-oriented and data transformation ways, functional programming makes a lot more sense. Coming from like the strict OO of like modeling and trying to have relationships and organizations of has a, and is a, and contains a, and has multiple, things like that. That's a very different programming style than the data oriented, which is one of my big, mind flip switches of, oh, this makes sense.
Can I make a comment?
Yeah.
Because I do a lot more with SQL and F#. First of all, the tooling for LINQ and F# is at a weird sort of point where it's more difficult to use than it should be, because LINQ is based on sort of the same concepts that you use in F#, and one concept that wasn't mentioned were these computation expressions in F#, where you can sort of create your own. It's the do notation in Haskell, where you can sort of create a mini LINQ inside of your F#. But on the other hand, some of the type providers are sort of in between status and may require a specific version of F#. It's not as well maintained as C# to LINQ.
Yeah, there are a lot of rough edges because it's a small community and it's developing very quickly in a lot of different directions. The tooling is hit or miss depending on what you're doing. Which is why I recommend stay with the core as much as you can. Because once you start getting into the interops and like the different pieces of language, things like computation expressions or quotations and things like that, there was a lot of meta object power on the periphery that I got by almost completely without, at least my first pass.
Thank you.
Yep.
So I actually have a question. So did the functional programming help with you have your physical system, right? If you want to add a sensor to this physical system, is it in your code? Is it easy to add a sensor, sort of using just using some bind notation or
I made it easy on a conceptual level, but I didn't actually build the syntactic tools to do so.
Yeah, so I'm kind of thinking you could have some add sensor function that takes as a URL as an input and then throws out and puts it into your big data structure, and then everything else is mapped over this new version of the data structure.
So because each new sensor has its own analysis, every sensor sort of has its own analysis package. I can't reuse a lot of the analysis methods from one sensor to another, because the analysis I would do on a viscosity sensor would be totally different than what I do on a light scattering sensor.
But if you had another viscosity sensor, it'd be
sure.
Or alternatively, if you had, if you wanted to do a computation, like a computed variable, like you were talking about, you could create one function that takes in an object and computes a variable, and then sort of use, binding or something to.
I always wanted to sort of do that. Right now, I have it where I sort of give it two of the portions of the record that I need it to, and then a function will give me that variable.
I see.
I haven't gotten to the part where I'm binding things and having automatically compute things based on things in my record.
Because it's sort of similar to, when I gave the talk, it was on this syntax in SWA, which is, but all of the sort of, the entire server is built out of these HTTP parts, and each of them does a little thing, and they all sort of work together, and you can sort of, I find that to be a useful pattern.
Yeah, and I think once I realized that that's what I was doing when I was just chaining functions together, and I was able to sort of lift all of that onto a similar level of abstraction and glue all those pieces together, it cut out probably a third of my code.
That's when it starts to sing. So.
That's when you're like, oh, I don't need to keep passing this all the way down. I can just apply it here, and it's a continuation all the way over there, and I don't have this massive chain of things going on. It's all working at the same level of abstraction. And that's a lot harder to describe unless you've done it. And that's sort of was like, what am I doing? This makes sense, but this is different. And I think it was that sort of, it took a while for me to understand why I would need to do that. Because if you had showed me, oh, this is how you propose functions, this is how you do this, I'd have been like, okay, how do I use that? Like, where would I even do this? But then once I start having those problems where I start having stringy functions and everything's calling each other, I'm like, I need a way to clean this up. Now, how do I put these two things together? Oh, well, this one puts out a function and this one takes it, and this one needs this value's output. Just put these all on the same line.
You can start folding together functions, which is
putting these things together, and it's like, oh, what used to be 3 or 4 separate functions is now implicit in the design of the organization. And it sort of is, the unseen structure is sort of what scared me as I said most, because there is a lot of structure. A lot of the OO structure is very explicit. It's really obvious what's connected to what and all those things like that. And a lot of the functional structure, at least that I sort of floated towards in F# was very implicit. It was, well, obviously these things take these things because that's the way to make it easy. And it was sort of like that path of least resistance is sort of where I felt. And in OO it was always, I would have to fight a little bit on the beginning and then it become easier later. And this was take the easy path to start with. And then, maybe I need to do some gymnastics later to transform to the types, but at that point that's hidden somewhere else.
Taking the easy path beats taking the hard path.
Yeah, more or less. I mean, not that I've gone far enough where maybe I did take a poor path, but at least it worked out for now.
It's really nice when you have those functions where it's like, this function is so easy to write. It's so obvious, like I know what parameters I need and I know how to combine them, and that's it.
And I know what the output needs to be. I had a function before where it was interpolating values when I lost data. So like if wires got unplugged or there was a short in the system or something like that, I would try to interpolate and save the data that came through even though I knew it was bad. And in C++, it was a lot of these special cases like, okay, this is if this thing faults and it does something like that. That was a function. It's like, oh, okay, the thing turns off and then we know it was good data, we want to interpolate it. So we want to use the data for just assuming some things. Like, oh, this is where it's intermittent data when there's performance problems and you're getting duplicates and then missing one. You can sort of throw those out in special case. And all those were like 50-line chunks each, and they all had to be using the same function to update the data. And I was like, it's like 200 lines of code. And once I could express each of those ideas and like interpolate over time, interpolate over bad section, interpolate over
Drop duplicates.
And then those just come together and that's 3 lines. As opposed to before when I was thinking of just conceptually modeling it, I was working at it of, I need this piece of functionality, it's separate, that's a new function, call the function the old function, move on. And sort of working at a higher level of abstraction, where things were easier to put together, made doing that work way easier. Refactoring was a whole different ballgame. Even the tools for F# for refactoring, not up to speed at all with anything else. Even the C++ refactoring in Visual Studio beats what F# can do. But manually doing stuff with text can do way more than what you can do. You have less text to work with is the big thing. And just a little bit of change can make huge impact, especially when you're working at the high level.
Do you use Visual Studio or do you use the...
I use Visual Studio.
I find, I don't know, I'm a big fan of like the INI project, and I find that it uses the compiler to do a lot of the things that Visual Studio does, and in some ways I think it's better than Visual Studio.
I was using Visual Studio before, so I already had things hooked up to like the VS Test
No,
Runner
that's
and stuff like that.
I actually, I go back and forth. I use the VS Test Runner, and I use, Atom for checking, basically like all the things that ReSharper does in Visual Studio.
Yeah.
So
Yeah, because I flipped between, because at some point I was like, oh, I'm using Microsoft stuff, I might as well go all the way. I started using TFS, and that was a bad choice. I didn't go into that.
I don't think Microsoft is pushing TFS anymore. So
No.
he use Git on Azure. So
Yeah. So, but a lot of the tooling stuff that I had just never really done into. But it was all fun. Again, I always try to like caveat all of my lessons that this isn't for like web stuff. I'm not trying to push this for like other things. I haven't tried Swab. I haven't tried a lot of other things like SQL type of library and things like that. So I try to limit my enthusiasm and my evangelism of the one functional language that I know.